Our next module is module number 5, strain energy. Now let us see what is the definition of strain energy and what is the meaning of strain energy. When an elastic body is stressed under the action of external force or load, it deforms and work is done on it. So which stores the energy within the body in the form of internal energy. This energy is recoverable when the stress is relieved, provided that the material remains perfectly elastic. So therefore, the definition of strain energy becomes the energy which is stored in the body due to straining effect or when the work is done on it is called strain energy. The strain energy is always positive and is caused by the action of either normal stress or shear stress. Uh, this strain energy principles are widely used for determining the response of various machine components and structures subjected to both static and dynamic loads. This strain energy is denoted by U and is expressed in joules or Newton meter. Therefore, strain energy is equals to work done. Now let us see a few important definitions related to strain energy. So first one, resilience. So resilience is nothing but the strain energy stored in a body within elastic limit under the action of external force is called resilience. So also it is the ability of a material to absorb energy within the elastic limit. So next one, proof resilience. So proof resilience is nothing but the maximum strain energy stored in the body without any permanent deformation. That is, if we load within the elastic limit is called proof resilience. Next one, modulus of resilience. So the modulus of resilience is nothing but the maximum strain energy stored in the body, or we call it as a proof resilience per unit volume is called as modulus of resilience. So it is mathematically represented by modulus of resilience is equals to proof resilience by volume of the body. So if we divide the proof resilience by volume of a body, so it gives modulus of resilience. So next we have a small derivation on the strain energy due to the axial load. So in this, the strain energy due to axial load, we are going to consider the two cases. So first one, when the load applied gradually. Second one, when the load applied suddenly. So what happens if we apply the load gradually on the strain energy, and if we apply the sudden load, so what happens to the strain energy? So let us see one by one. So let us consider the first one, when the load applied gradually. So for that, let us consider a prismatic bar subjected to axial load, that is tension. So as shown in this figure, when the load is applied gradually from 0 to F, the extension of the bar increases. In the right hand side we can see the bar is extending by an amount delta. So thus the load F does work, so which is shown in the figure by the dotted line. So in the next diagram, The vertical line represent the axial load or load, and the horizontal line represent the corresponding extension of the bar. So the diagram will be straight line up to the elastic limit. Since we are applying the load gradually from 0 to till its elastic limit, so there is a straight line. So area under this straight line represent the amount of work done. So let F is equals to gradually applied load, and L is the length of the bar, prismatic bar, and delta is the extension of the bar due to the application of load F, and A is the cross sectional area of the prismatic bar, E is the Young's modulus of the bar material, capital U represent the strain energy, sigma is the stress induced. Next, so to find the work done due to the gradually applied load, so work done is equals to area under load extension diagram. So this area under this load extension diagram gives the amount of work done due to the gradually applied load. So since it is like a triangle, so area of the triangle becomes half into base into height. So half into base is, suppose if I consider this as a base is F, whereas height is the delta. So we know the extension delta can be written as FL by AE or PL by AE. So in place of delta, so I'm going to substitute FL by AE, and whereas this F can be written as sigma into A, because we know stress is equals to force by area. So therefore force can be written as stress into area. Now, so in this equation, so F by A can be written as sigma. This F by A can be written as sigma, and retain this L by E as it is. So therefore sigma into sigma becomes sigma square, and in the denominator we have E. Then so this becomes volume, area into length becomes volume. This area into length becomes volume. Therefore the final equation half into sigma square E into V. So but we know from the definition, strain energy is nothing but work done. Therefore above equation can be written as U is equals to sigma square divided by 2E into volume. So the next one is the second case, that is when the load applied suddenly. So what happens when the load applied suddenly? So to derive the work done due to suddenly applied load, consider a bar subjected to suddenly applied load. So instead of the being applied gradually, so we are applying the uh, sudden load. So when the load is suddenly applied to the body, the load is constant throughout the process of extension of the bar. Also, in this process, no change in the displacement and nature of the strain energy. So therefore, the graph becomes like this because we are applying the sudden load. So to find the work done, so let us consider the same diagram, because area under this diagram gives the work done due to the suddenly applied load. So work done is represented by U is equals to, so area of this one is length into breadth. So length is F, whereas breadth is delta. So we know that extension delta can be written as FL by AE. So therefore in place of delta I will substitute FL by AE. F by A is nothing but stress. So directly I will substitute sigma in place of F by A, and I will write as it is L by E. let me call this one as equation number 1. Next, so strain energy due to gradually applied load. So in the previous case, that is gradually applied load, so we got strain energy U is equals to sigma square divided by 2E into area into length. So in place of volume, I'm writing it as area into length. So call this one as equation number 2. Now I'm going to equate equation number 1 and 2. So therefore, so this is equation number 1 and this is equation number 2. So here sigma and sigma square get cancelled, length get cancelled, Young's modulus get cancelled. So I will write the remaining terms in the next step. F is equals to sigma by 2 into A. Therefore, sigma can be written as sigma is equals to 2 times of F by A. So therefore, stress induced due to suddenly applied load is twice the stress induced due to gradually applied load. So next one, strain energy due to shear. Now let us see uh, what happens if we apply the shear stress to the rectangular element. So let us consider the rectangular element ABCD of length L and height H. So which is applied by a load F on the surface CD. So due to the application of load F, there is a change in position of C to C dash and D to D dash takes place by an amount X by an angle phi. So if we plot the graph by taking extension along x-axis and load along y-axis, so we will get a linear curve like this, a straight line. So area under this curve or graph gives the work done. So along x-axis we have the extension x and along y-axis we have the applied load F. So here tau represent the shear stress induced at the top face CD and phi is the shear strain and G is the modulus of rigidity of the material. A is the cross sectional area of the face. So that can be determined by length into breadth. So from this diagram, shear strain can be determined by considering the triangle ACC dash or BDD dash. So if I apply tan trigonometric rule, so what happens to this triangle? So tan phi is equals to opposite side by adjacent side. So opposite side is CC dash, adjacent side is this AC. CC dash is nothing but X, AC is nothing but H. Suppose if this angle is very small, so directly we can write phi is equals to X by H. So next we know work done is equals to area under load extension diagram. So area of this diagram is half into base into height. So base is F, height is X, therefore half into F into X. So here X in place of X we can substitute X is equals to phi into H. So in place of X we can substitute phi into H, and whereas this F, we know shear stress is equals to load by area. So load is nothing but tau into A. Therefore in place of F we can write tau into A. In place of X we can write phi into H. So therefore above equation can be written as tau into, so area is nothing but L into B, L into B, phi into H. So length into breadth into height is nothing but volume. Therefore, in place of L into B into H, directly we can write capital V. And we know that modulus of rigidity definition G is equals to tau by phi. Phi can be written as tau by G. So if we substitute pi value as tau by G, so half into tau by G into V, above equation becomes half times of tau square divided by G into volume. So therefore, so work done becomes U is equals to tau square divided by 2G into V. So this strain energy is the same as the strain energy due to axial load, because there we have normal stress sigma and Young's modulus, but in this case we have shear stress and modulus of rigidity. So next one, a strain energy due to bending. So to derive the equation for strain energy due to bending, consider a simply supported beam of length L and uniform cross section area is subjected to gradually increasing bending moment. Okay, so as the bending moment increases, angular rotation and curvature in the beam also increases. So we can see in the second diagram. So as the bending moment increases, the angular moment phi and this curvature is also increases. So it can be represented by a graph by taking x-axis as angular rotation and y-axis as a bending moment. So it increases gradually, therefore there is a straight line. So area under this curve or graph gives the work done or strain energy. So let us consider M as capital M as applied bending moment, R is the radius of curvature, and phi is the angular rotation. Sometimes we call this one as flexural rotation, and E is the Young's modulus of the beam material. I is the moment of inertia of the beam cross section. So next one, so we know that work done is nothing but area under the load extension diagram. So from the load extension diagram, off into base is M, that is bending moment, and height is phi, that is extension of the beam. So from the previous diagram, so phi can be written as that is, so we have L, length L, so L can be written as phi into R. So therefore phi can be written as L by R. So let us call this one as equation number 1. So from the flexural formula or bending equation, so M by I is equals to E by R. So this one we have derived in the module 1, that is bending equation. M by I is equals to E by R. So therefore 1 by R can be written as M by EI. So if we substitute this one in the first equation, so the equation 1 becomes M square, because here also we have M terms, M by EI. So therefore if I substitute 1 by R in the first equation, equation number 1 becomes M square L divided by 2 into EI if the beam is loaded with concentrated load UDL couples, then bending moment varies along the length. Okay, so assuming the bending moment is constant across the length, small length dx of the beam, the strain energy due to bending is given by, so EU is equals to integration from 0 to L m square into dx divided by 2 into EI. So next derivation is strain energy due to torsion or twisting moment. So to derive the strain energy because of this torsion, let us consider a solid shaft of diameter d and length capital L subjected to gradually increasing twisting moment capital T. As the twisting moment increases, the angle of twist theta increases correspondingly. So where capital R represent the radius of the shaft. So if we draw the graph by taking x-axis as angle of twist and y-axis as torque, so it increases gradually. We'll get a straight line from 0 to till the elastic limit. And so if we consider the area under this graph, so it gives the strain energy due to the torsion. So here also we got the triangle, area of the triangle we have to consider. So before that, so let capital T is equals to applied torque, R is the radius of shaft, J is the polar moment of inertia of the shaft cross section, tau is the shear stress at radius R. So from the torsion equation, so we know the second case, T by J is equals to G theta by L. So we have derived this equation in the module 4. So we can write theta is equals to T by L is L by Gj, and we know that work done is equals to area under torque angular twist diagram, that is half into base into height. So base is a T, that is torque, and height is theta. Therefore half into T into theta. So in place of theta, we can write this one T by TL divided by Gj. Therefore half into T into TL by Gj. Therefore the work done or strain energy becomes U is equals to T square L divided by 2 into G into J. So next one, strain energy due to impact load for axially loaded members. So impact loads are produced when two objects collides or when a falling object strikes the structure. Consider a vertical rod fixed at the top end and having collar at the lower end. Let the weight W be dropped from height h onto a collar at a lower end of the rod as shown in the figure. When the weight is dropped on a collar, it will produce a maximum instantaneous extension delta in the rod, and will therefore we can say that work has been done. So this work is stored in the form of strain energy. There are three specific assumptions are made. First one is the weight W falls freely. Second one, the support is rigid. And third one, falling weight does not bounce off and no loss of energy on striking the collar. In practice, the striking body does not transfer all energy to the rod. So if we plot the load extension diagram by taking extension along x-axis and load along y-axis, so we'll get a straight line like this. So area under this graph gives the work done. So let capital W is equals to falling weight, and small h is the height through which weight falls. Capital L is the length of the rod. A is the area, cross sectional area of the rod. Sigma is the impact stress, and delta is the extension of the rod. So work done by the falling weight on the rod becomes equal to the strain energy stored in the rod. So here the work done by the falling weight can be written as W is equals to W into H plus delta. So H is the height through which the weight is falling. Delta is the extension takes place due to the falling of the object. Then the area is half into base into height. So therefore, so delta is nothing but FL by AE or PL by AE. So P by A is nothing but sigma. So directly, so we have written here sigma, and as it is we are writing L by E. So here half into, so P we are writing as it is, and in place of delta, so sigma L by E, because FL by AE. So therefore, so if we multiply W, it becomes W into H. Then sigma we can take outside, WL by E, and here also sigma square, because this P can be written as F into A, so it becomes sigma square, then AL by 2E. So we can rewrite this above equation as sigma square into AL by 2E minus this term sigma into WL by E minus the remaining term WH is equals to 0. So it is like quadratic equation. We can write the, or we can find the roots of these equations. So it is like ax square plus bx plus c is equals to 0. So we know the equation minus b plus or minus root of b square minus 4ac divided by 2a. So therefore the roots become, so sigma 1 comma 2 are the roots. So WL by E plus or minus root of WL by 2E the whole square plus 4 into AL by 2E into WH divided by 2 into AL by 2E. So after simplifying the above equation, so sigma 1 and 2 becomes, because these are the roots, W by A plus or minus root of W by A whole square plus 2EWH divided by AL. So we can take WA as common. Therefore above equation becomes WA into 1 plus or minus root of 1 plus 2HAE divided by W into L. So if we take the positive value for maximum stress, the above equation becomes, so only we are considering the positive value. Therefore sigma 1 is equals to W by A into 1 plus root of 1 minus 2HAE divided by W into L. So if H is equals to 0, that is height through which the object is falling is equals to 0. So this above equation becomes sigma is equals to 2w by a. So which is the case of a suddenly applied load.